In this lesson, we're going to look at our solution for the block oscillator. Namely, I'm going to skip down here to the middle for a second. So we need to have x equals a cosine omega t memorized, right? Because that's our empirical result. And again, I have down here, but let's reinforce it. Time t equals 0, we begin our stopwatch. We're at x equals positive a, no phase shift. Well, what we're going to do now is show that this equation is a solution to the block oscillator. How are we going to do that? Well, the language here is important because for the AP test, they may give you a question that says, write down the differential equation of motion that governs the block oscillator. Let me repeat that. If you are asked to write down or to derive the differential equation that governs the motion of the block oscillator, you are going to follow the analysis path and procedure that we are using here. Ultimately, what we are going to show on this page of notes is a proof by substitution, which is a valid mathematical proof. In other words, we are going to show that our equation, if substituted into the equation that governs the motion of the block oscillator, satisfies this equality, then we have a valid solution. We do not necessarily have a unique solution. So this proof does not prove that we have a unique solution, but it is absolutely a valid proof that we have a valid solution. And along the way, we are going to show that this equation, x equals a cosine omega t, has to also correspond to omega equals the square root of k on m, the spring constant k in mass. We'll talk more about that as we go along as well. So we'll get to that. But back to our differential equation of motion that governs the motion of the block oscillator. Well, anytime you are asked to write down the differential equation of motion, you are going to start with Newton's second law, F equals ma, and you are going to put it into calculus form, where you have F equals m d squared x, second derivative of x with respect to t, d squared x dt squared, or in other problems, it would be F equals m dv dt. But since our solution is an expression in terms of position, we are going to leave Newton's second law in terms of position. If we had a velocity function here instead, then our F equals ma differential equation would be F equals m dv dt. Well, we know Hooke's law, F equals minus kx, and we know Newton's second law in calculus form, which is our differential equation form. I know you haven't had differential equations yet in math, but trust me, that is the differential equation form. We simply set equation 1 equal to equation 2, and you are done. You box that equation. That is the differential equation that governs the motion of the block oscillator. So please, 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 please get this into your notes. You can explode it if you wish, as I am here, because that is language you may see on the AP test, and I do not want you flustered by it. Okay, what we are going to do is do our proof by substitution. We are going to take this x and substitute it in for x. We are going to take the derivative of this position function twice to get d squared x dt squared. We are going to substitute that in to the right-hand side. So if you've forgotten how to do your derivatives of cosine and sine, please look on our last page of notes to verify that that is the acceleration, d squared x dt squared. When we do that, we get some very nice cancellation. We see that we get the A cosine omega t, the whole position function, cancels with an A cosine omega t over here. And look, what falls out is that for this equality to be true, we need to have omega squared equals km, or omega equals the square root of k on m, and this is shown to be experimentally true. Now, I do want to spend just one quick moment here talking about what does this equation really show us. Omega is equal, as it says down here, to 2 pi f, and we know now it also equals the square root of k on m. But what is this telling us? The frequency is telling us how frequently the oscillator is going back and forth, back and forth, back and forth. So the higher the frequency, the faster it's going back and forth. Well, what makes a block oscillator go back and forth really fast? Well, if we think about it, one thing that makes an oscillator go back and forth really fast is a strong spring. So if you stretch that spring a little bit, it's going to pull it back to the center really hard. The other thing that will make this move really fast is if we have a very light mass, very little inertia. So the square root of k on m makes sense conceptually for how we know nature works. And the last thing that I want to point out on this page of notes that is very important, often a multiple choice question on the AP test. So there's a lot on this page of notes that is often on the AP test. And that is that if we look at the expression for the frequency and the period of motion in simple harmonic motion, we get the result that the amplitude does not appear in that equation. So it does not matter whether we pull the block 1 centimeter and stretch the spring 1 centimeter, or we stretch the spring 2 centimeters. The frequency of oscillation, the amount of time it takes to get back to where you started, is the same, and we can understand that conceptually by the fact that the spring pulls back a lot harder the more that you stretch it. But that notion, please, again, if you can, explode that one out for yourself. That often appears on tests or anytime we're studying this unit. So let me clear out all my extra markings here so you can make sure that you get all of the annotations that are down on this page. And very, very important that you are proactive and ask questions if any of this is questionable to you.